Good morning or good afternoon.
Good afternoon, sir. It's a pleasure and honor having you today. Whatever the time is, it's afternoon in Cairo, but I think it's already early morning.
It is early morning for us, and it's afternoon there, and it's a good afternoon to you. And I'm just very honored to be here.
Yeah. Thank you for joining us, Professor Khalid. Would you please start the session? Introducing Professor David. And
okay.
Thank you.
In the name of God, the most gracious, the most merciful. Initially, the Faculty of Computer Science and Information Technology at MIUCC University had the honor to hold its first international scientific conference. Really, what makes me more honorable is the presence of Professor David. Professor David Allen is a writer, author, and speaker on issues of technology, society, and organization. Actually, the author of numerous award-winning books of computing and society, including When Computers Were Human, the story of how we organized competition before we had machines to do for it. He is a fellow of IEEE, the Institute of Electrical and Electronic Engineers. He received this award for his contributions to crowdsourcing since 2007, written a regular column in Computing and Society for Computer magazine. He has served in a variety of leadership roles in the IEEE, including manager of Computing Society magazines. He was a vice president of the publication for Computer Society and the president of the Computer Society of the IEEE at 2013. He has been employed by George Washington University in a variety of professional and administrative roles. He is currently a professor in the Center of the International Science and Technology Policy of the Elite School of the International Affairs, so that we can enjoy together the interesting lectures that he will kindly give to us for a period of about 40 minutes, which has a topic title,
The generation of computing and the coming data age. It includes the development of computing and the Grier generation cycle, starting with mainframe generation, software or PCs generation, followed by internet and mobile generation. I have a lot of things to say, but I am not going to take more time. So you enjoy all benefit from keynote speech from Professor David. It is honor pleasure to start the speech, Professor David.
Yes, Professor David, please go on. It's an honor for MIU to host you this keynote speech. We will enjoy a very fruitful and important speech from you. So please go on. May I ask Professor Khalil to stop sharing, if you please?
Yeah, sure,
Professor
sir.
Yeah, if Professor David would like to share.
Okay.
Thank you very much. Please go on, sir.
Thank you. I may share my screen now so you can see my slides.
Yes.
Okay. And I am clicking.
You can go, sir.
And you can go and you can see my slides.
Yes, sir.
Yes.
Very good. Thank you so much for having me here. It is an honor for me to be speaking to you, and I hope I live up to that honor. Because of my role in the Computer Society and the positions that I've had, I'm very interested in leadership and where the field is going and what kind of qualities that leaders will need to deal with the technical problems that we face today and that we face tomorrow. And so I'm talking about really generations of leadership and the kinds of leaders that you are going to become, because you are the next generation of leadership. And I have concluded that the qualities that you will need and the qualities that the next generation of leadership are first slightly different from those that we face today. And second, it follows, though, in a great tradition of what computer science and computer engineering have been, and it builds on a tradition of dealing with certain kinds of problems and expanding the ability of this field in which we all work and have all been part of, to deal with new problems, bigger problems, and problems that touch the lives of more people in useful ways. I'm calling the topic the nth generation because for many years we have asked the questions, what generations of computers do we have? What generation of software? And we sort of have lost track of it, but I'm interested in what generation of leader. And let me make sure I can do it. Here we go. What really causes us to start to think about this is that we are seeing the convergence of 5 technologies that are working quite closely together to support a new way of thinking about problems. The first of these is cloud computing, which involves a number of things that we've known before, the centralization of computing services being only one of them. Part of it is the ability to buy services that you need, which is something that has been central to computer science for 60 years, and having it available ubiquitously, any place you need to go. When I was president of the Computer Society, we were putting together our big initiatives on this, and it was something that we clearly saw as the future, but we didn't quite see how all the pieces were going to work together. Another thing that we were working on at the same time, in roughly 2013, 14, 15, was the Internet of Things. In addition to having computing being ubiquitous, having it be everywhere, we were starting to appreciate that we could gather data from a lot of different places and collect it and put it together. And that many things would gather data that we had not thought about gathering data. At this stage, we had had phones for some time, and we knew that we could gather location of phones and the calls, but we hadn't thought about the motion the phone has, things that we now have with the digital watches that track what we do, our activity, our heart rate. We hadn't thought that every little utility might have an internet connection, every small appliance, and that we could gather a variety of data from it. And we also didn't quite see that that data would be merged with cloud computing, in particular in the new example of cloud computing that talks about edge and fog computing, because of the fact that we would be storing a lot of this data out in the edges of the cloud, not in a central repository. So that's been a new thing that has worked together. And with those two, obviously, big data has been part of it. Big data is a little bit older, and it came largely in dealing with commercial data at scale, and a recognition that we would not have all the data in one place. One of the great lessons of the last 15 years has been that it's cheaper to compute than it is to move. It's roughly a factor of 10. To move data from one data center to another, the distance matters, but not a lot. The basic problem is just getting things moving and then getting it at the right place. The amount of energy that requires is 10 times the amount it takes to compute a simple operation with that same data. So our thoughts have been increasingly to think of how do we use this data distributed around the world and how do we connect it? And those 3 pieces now start to work together. We have cloud computing, the ubiquitous computing that provides us, Internet of Things that gather us, and big data that takes it and finds the techniques for working with it in a distributed form. Crowdsourcing. A little more than 10 years ago, I discovered that I was an expert on crowdsourcing and that I was one of the world's great experts on crowdsourcing. And that lasted about 3 months. I was an expert because I had written a book on organizing computers and people and how the two worked together. And that's in many ways what crowdsourcing does do. And it does it with marketplace models and other forms that allow large groups of human beings to work together. At the time, we were looking at it with things like Uber and Mechanical Turk and other things that did certain tasks. But increasingly, we have discovered that it's quite useful for dealing with data. in particular with preparing the kind of training data that we need for machine learning. And the picture here is one of the Samasource crowdsourcing operations. I believe it's in Kenya. And this has been the big growth of that form. So it's something that is doable because of things like cloud computing. It deals with data we gather from Internet of Things and other places. And of course, it is a big distributed data set, and it's largely used with processing it, with labeling it, with identifying the data that is useful for machine learning and that is going to help us advance machine learning, which gets us to the fifth technology, machine learning. Machine learning is not new by any stretch of the imagination. Artificial intelligence as a field comes out of the mid-60s, and it's really part of the drive that builds computer science and that moves computer science away from numerical analysis. It provided an awful lot of very interesting algorithm developments that have permeated throughout the field and are used in things that we no longer think of as intelligence. The simple routing algorithms, we now think of them as simple, that we find in map applications, that we use for transportation. They came out of artificial intelligence in the 60s. And there was a recent meeting I had with a group of experts from that era. And we asked the question, what's your biggest contribution? What's the one thing that you have done that changed the world? And they said to a person, A-star search. And that's exactly the search that we use for guiding through a map. Machine learning brings a new scale to all of these things, because these are, in particularly the data side of things, the data, the Internet of Things, the cloud computing, provide a flow of data that was unimaginable 40 years ago. And we have learned in the process that it's very difficult for us to deal with it with the techniques of 40 years ago, that we have to have an automated way of finding patterns, of making decisions, of processing it, of thinning it, of identifying typical examples, of suggesting what kind of actions we need to take. And that's the role that machine learning is providing for us. All of these lead us towards innovation at scale. And ultimately, they are doing what computer science has always done. They're capturing human experience and trying to mechanize it, trying to do it in a way that provides us with services that help our daily lives, that improve our ability to feed and clothe ourselves and our neighbors, that gives us new opportunity to build wealth, to bring us closer together, allow us to understand each other, and to see good wherever we can. The bottleneck for generations has been, how do you devise the instructions, the program, the system to do this? And these things working together provide a big flow of data, provide a platform on which to process it, and provide us with the tools for reducing that programming time by capturing human experience with as general a program as we can do, and from these algorithms, determining the ideas and the value that we have in that data. So these are the questions that I'm interested in looking at. What is the nature of the field? I was at, not that long ago, a computer science research retreat. It had the leaders of computer science departments, academic departments, from most of the world's big research institutions. And they were discussing, where's the field going? How should we develop our faculty? What do we need to do? And one chair got up and he said, I don't know if I'm the only one that feels this way, but I feel that the computer science that I learned in the 90s is drifting away, and that a new computer science is coming in. And what's to happen with what I learned? Am I now obsolete? And it was a very heartfelt plea, but it really pointed to the question of where the field is going. In that, who is the leaders of the field? What kind of person do we need to take charge and guide the rest of the field forward? And all of this swirls back on the foundation of what's the intellectual foundation of computer science. What do we do? What gives us validity? Initially, computer science was a mathematical field, and mathematicians felt that they were going to dominate it. Electrical engineers stepped in very quickly because, for a period, electrical engineering was the major interesting question of it. What's the foundation today, and how is it different from those? There are many people who talk about technology generations, and we go through many different ways of measuring that. One of the things that has dawned on me as I've worked on my career, and as I've served in leadership roles for the Computer Society, and also I should add, in looking at my father's generation, because my father was a computer scientist as well. He joined the UNIVAC Corporation in 1957. And through that connection, I had a firsthand window of his generation of computer scientists and what they did and what was important to them. It also taught me that our careers are fairly short. Academic computer scientists tend to be at the lead of the field for roughly 15 years. If you're in business, you can be in it a little bit longer because what you end up doing shifts. And you may start your career needing to be at the head of the technology, but by the end of it, you're much more valuable as someone who's helping lead people and shaping an organization. If you do that, you start to begin to see that if we do 20, 25 years, that we are probably in the fifth generation since 1946. And we have seen handovers from one group of leaders to another. This picture I have here is the first generation of computers. This would be the group of people who worked in the late 40s and early 50s. If you are not familiar with this picture, you should be. The man standing in the corner is John von Neumann, the man who invented the basic structure, the basic model for computing that we have used ever since, the von Neumann processor. And that machine that he's standing next to, it's his computer. He designed it and he built it. And that row of cans across the bottom, that's memory that can store, each one of those cans can store 1,000 bits. So you count up, and this is not the biggest of computers. But these people built their own. They were coming to grips with the basic concepts of the field. Following them, a second group came when computers became a product. This happens in the mid-50s, and I'll have some more specific dates as we go on. These were people who worked for IBM, for General Electric, for Siemens, for Ferrante, companies around the world. And for them, a computer was a product. It was largely a factory product. It was something big that you put in a control environment, but it was something that they could work with that was uniform, and you could start to develop skills across organizations that could use the same machine. The third generation starts lowering the capital cost. It includes operating systems, which is the key bit, which means that many people can use the one system. And more importantly, you get just as much computing as you need. In case you wondered, that man in the middle of that picture is my father. And I've always thought of this as his family portrait with his computer standing behind him. Following that generation, we move into the microcomputers, the desktop computers, things that were small enough that individuals could own. And that was a key bit, again, in shaping the field. I'm sort of tracing out hardware here, but the real issue is not hardware. It's thinking, it's concepts, it's where the field is going. Since the last, since 2007, 2008, the mobile phone has been the major platform for computing. We have a cloud environment behind it, of course, but that has been the identifiable platform for computing. And what is fascinating, says he who has had a long career with Computer Magazine, is that we knew it was coming and we were surprised by it. If you look at Computer Magazine in 2007, 2008, 2009, and I can speak with authority because I was on the editorial board then, We knew this was going to be an important thing, that it was going to be interesting. We did not think it was going to move into the market as fast as it did. We did not think it would change training as fast as it did. We were offering courses in app development by 2008 and 2009. And we didn't think that that would become the dominant entry point. And that has been just a fascinating rise of how fast that has happened. All of these are technologies, of course. And as technologies, we start to see common themes across them. One question that starts at the beginning is efficiency. And computer science is deeply involved in the question of efficiency. Time, cycles. How much work can you do in how few cycles of a computer? When you are John von Neumann, and it's 1948, and you are dealing with a memory unit that holds 1,000 bits of memory, you need to be very careful about how many instructions you execute and also how much space you use, how much memory. Second becomes not only efficiency that of time and space, but at some level, distance. In 1948, we were already thinking about networking, or more accurately, transmitting data over phone lines. And that was going to be an expensive thing. We knew that. And the question is, how could we minimize the moving of data? But at the same time that that is grinding out, a second series of themes are starting to come out in computer science. And those are themes of universality. It's hard to imagine, and it's one of those things that I do this old guy, you don't remember, my children, when every computer had its own instruction set and when every vendor had its own variation of Fortran or Java or whatever language we were programming in. That applications written for one computer would not work easily on another. At best, we have the difference between iOS and Android operating systems. That's the closest we come. But even those are relatively similar given the differences that we had. And so computer science gets involved not only with this idea of how efficient can you make machines, but how universal can you make them? And if you trace the literature through the 60s, you find constant efforts to try and make computers a more universal device. The next theme that comes out is processing at scale. And from the beginning, we are looking at the idea of how big a problem can computing tackle. That has been the main theme behind high-performance computing. High-performance computing, at some level, all computing is high-performance computing, but it broke out to be a separate field in the mid-1970s. Initially, it was dealing with the kind of problems that could afford to pay for expensive computers, problems that involved national defense, that involved weapons design, that involved fundamental research for weapons design. But from that period, I'll date it to roughly 1977, it has grown to be an independent field that has largely looked at computer architecture and to some extent different technologies as quantum becomes more important, on how to handle massive scales of data. And when you're looking at basing judgments on the outcome, and that you need to understand data from a region, from a country, from a continent, from the world, you simply can't handle that by hand. In theory, you can. I mean, in theory, you could get enough people together. But in fact, you can't do it fast enough to make the kind of judgments that are valuable. There was a fairly famous writer in the 19-teens and 20s who put together the method for numerical weather prediction. And he said, it's very, very easy how we do it. We rent a football stadium and we put everyone in it. We fill all the seats and we put the calculations on pieces of paper, and people will do their calculation and they will do it for a small part of the world. And that will be represented by where they sit in the football stadium. And then they will pass their paper to the person sitting to their left, which represents someone to the east of them. This was a northern hemisphere writer. And the person to the east of them represents someone just a little further on. They will do their calculation and pass it on. And so you'll have this swirl of paper circulating the soccer stadium. And that uses the same kind of methods that we still use, not quite as finely done, obviously, but also for the obvious thing, even at the crudest model that you would do at that scale, you would get, a 24-hour weather prediction, tomorrow's weather. You could predict that in roughly 3 to 5 weeks. So the weather would have moved on and you wouldn't have completed it. So computer science very much has been involved. How do we get up to scale? How do we get up to speed? How do we automate methods? How do we do this to get a common set of methods that can handle different problems? So if that's the core of it, we then start to look at what are the skills that you need to develop these methods. Mathematics was once the dominant method, and mathematicians once assumed that they were going to be part of computer science, or more accurately, that computer science would be part of mathematics, and that was it. Initial computing departments were once called mathematics departments, and it was generally assumed that the training for it would be mathematics. The 50s and 60s taught us that programming was a different field, and that there were a lot of things that interested programmers that simply didn't interest mathematicians, and that was going to be a key part of computer science. Roughly 20 years later, programming moves into system integration. Operating systems time sharing largely drives this. And the idea behind it is that we can build different pieces and have people specialize in one aspect of a system and then connect those pieces together. We go ahead another 20 years to the 80s and we discover that system design becomes interesting, because the question becomes, how do you plan this? How do you do it in advance? How do you deal with those issues of efficiency, of time and space and distance, to make a full system that may involve not only computers, but sensors? It may involve people, and it certainly involves large amounts of data. And we've seen since the 90s just a greater and greater interest in data architecture. How do we set up our data flows and our data processes to make this whole thing work? This set of skills, and these aren't by any means all of the skills of computer science, represent some of the clear march forward that you all are taking part of, and that your classes, your first jobs, your leadership, the departments that you lead, all of these are taking part in asking the questions, what are the next set of problems, and what are the next skills that we need to have available to us to solve these problems? Again, we are driving towards efficiencies. We are driving towards what makes the best use of our systems and our machinery. This, as I said, has been true since the beginning. And we have always had a group of people that say, 5 years down the pike, we will have so much computing power that it won't matter. We have discovered that that's somewhat true and somewhat false. I have 2 laptop computers that I use all the time, and that means each one of them is not entirely employed. I will often have one rendering files or rendering presentations while I'm working on the other. But it means I have more computing power than I use 24 hours a day. That's good. That gives me choices. That allows me to do things. At the same time, we know that our major data centers are working hard, that they're consuming lots of energy, and that we have need for more and more of them, especially if we are to expand what we do. These technologies and these ideas, which I've only sketched generally because you all are involved in them, and for me to get off and get into details, you would all be sitting there going, he's not up to date. And I'm not. But I see the big patterns, and that's what interests me. What really interests me is you, what you're going to be doing, how you are going to shape the questions, because that's what leaders do. Leaders, if you are working in the field, your job is to answer questions. If you're to be a leader, you are to say, this question is important. The issue that you are interested in is important, but I would frame the question this way. As president of the Computer Society in my work, in the Computer Society. I've gone to a lot of conferences, and I go to a lot of regional conferences. And I can't say how pleased I am to be at your conference and your first international conference, because it shows you embracing a bigger and bigger world, because that involves questions. If you're working at a regional conference, you can ask the questions that interest you and interest the community around you, and you don't really have to care how well they fit into the questions that others in the world are asking, and particularly people who might be leaders in a different part of the world. Now you do. And now that means you are moving forward, and you are constantly asking, what's our perspective? What do we see as important? And how do what we see important shape questions for the entire community, for the entire world to engage? That's what you're involved in, setting ideas and setting questions for the entire community. What are the goals that these questions suggest? What are the methods that will answer these questions? And most importantly, and this is something that in my students for years I did, I would sit, and to be honest, I also did it as president, but I was nicer. With my students, you can be a little firmer. I would see a student give a demonstration or a pitch or do a final report on their project. And I would sit back and I would be very gruff and I would say, so what? Why should I care? And they would go back and they would repeat what their system did and how they had gotten great timings or whatever. And I would say, tell me the advantage. Tell me why I should use this. Tell me the benefit. Shape the answers that you are getting from your questions in terms of benefits for yourself, for your lab, for your community, for the world at large. And that's what it takes to be a leader. And that was what I was interested in training. So getting those things together, the goals, the methods, the advantages, are what shapes a leader. As I said, I have looked, and there's a certain arbitrary nature of defining leadership generations. But there have been, as I've said, 5 or 6 since the start of the field. The first one was relatively short-lived. It comes out of mathematics. If you are not familiar with Admiral Hopper, that is the woman that you see on the screen in front of you. She worked for the Navy, US Navy. She was involved in developing several of the very first computers. Her first 2 were entirely mechanical, well, electromechanical. They used stepper motors and relays to do the calculations instead of transistors or even tubes. And the question of what kind of ideas did she follow? What did she know about? She was a mathematician. She learned her computing experience by working with punch card tabulators. And the kinds of writers that shaped her as a leader were the writers of Chester Bernard, who was the head of the American telephone system in the 1920s and 30s. Bernard was very much interested in how you take a big problem and divide the labor across thousands of people, something that would support the American telephone system across the continent. And those ideas of how you divide the problem shaped Admiral Hopper and the people around her to thinking about how you include a machine in that, how you move beyond mathematics to create systems that would use mathematics, but solve a broader class of problems. The second generation is longer. It's the one that includes my father. It lasts from the early 50s. 1952 is the time computers become a product, when you could go to an office and say, I want to buy a computer. And they would say, sure, we'll sell you one. The leader here is Thomas Watson of IBM, very influential leader. His, the person that he would be following would be Peter Drucker, who was a writer on business and organizations in the 50s. And he trained that generation. And he trained them to really think not in terms of individual processes, but organizations. How you fit something into a company, a government agency, a university, and how you make those pieces talk back and forth. He was highly influential. He wrote about 38 books. His big fat one, Management, was read by everyone in that generation. And you see it in terms of thinking about these big computers. How do you fit them into the organization, and how do you make that big computer do work for that organization? That generation started retiring in the mid-70s, and it was replaced by a third generation of leaders. Now, I know let me back up here a moment. In the generations that many people say, this is slower, but nonetheless, I think in terms of human leadership. The third generation emerges in the 70s, Steve Jobs, obviously, and it includes Bill Gates and the others following him. They read works by people like Tom Peters, who were very much interested in empirical management and empirical organization. And with Peters and with others, the question became observing, gathering data, and trying to understand what's going on in the organization. And he was very much interested in software as the point of organization and at point of innovation. And at this point, that's the shift that happens. Software becomes the key item. Fourth generation begins around 2000, and we are still in the middle of it, although I think we're coming to the end. These generations last roughly 20 years or so. It's the group that did the first round of the mobile cloud apps for computers. It has a variety of leaders that would include Mr. Zuckerberg. And this group really has started the shift into ubiquitous computing and computing everywhere and data being the point of innovation. The literature that they read would include works by people like Clay Christensen, who argued that innovation was an essential part of growing any organization or any field. And this is the key point, that innovation involved shifting, in effect, abandoning old methods and embracing new ones. His common phrase was disruptive innovation. Disruption meaning you're changing the organization, you're changing processes, you're changing technology. If we go back over the quick thing, Bernard saw computers as factories, as something that were part of a traditional manufacturing process. Drucker saw structure as important, that you just moved computers out into the organization and you started empowering individual groups, and that computing was a service, it wasn't a thing. Peters saw continuous improvement and saw the idea that you were always working to make your system better, to advance it, and the ideas of agile development, which in computer science really come out, 1995, 96, 97, 99 is the Agile Manifesto. He's laid the groundwork for that and saw that that was a process that was coming. And Christensen, as I was talking earlier, talked about reallocating resources, that none of these things were fixed, that there was always going to be disruption whenever something new came along. So that leads the question for you. We've got 3 years. What is your generation going to be? Who are its leaders going to be? And it's a little bit shocking to think that this means abandoning Mr. Zuckerberg, that his time has passed. He will probably be with us for a little bit longer, but his time has passed. The world that he shaped exists. What's the next world? That world clearly, given everything we've seen, is based on machine learning, both of the two major sorts, both the supervised machine learning, which involves the crowdsourcing, the data gathering, the training, a lot of work that we understand fairly well now, and we're starting to move that into college education. And the untrained machine learning, which we don't understand as well. We know it from data mining and some of the work of the big data of the 90s, but that's not quite as stable, and it's not quite as clear how it fits into our world. So those are the sort of things that we see. What are the leaders going to need? Speed is clearly an issue. Being able to change and upgrade and develop new systems and build on old systems is going to be vital. Efficiency is going to be vital. Universality is going to be vital. What are the leaders of that going to read, and what are they going to do? And that's the question I can't completely answer. I'm starting to see some ideas, but it's not clear to me exactly what the result is. Some of the things that we're seeing, though, is a weakening of structure. Organizations consist of a group of people, and each of those people have three things: position, function, and structure. Position is where they fit in the organization, function is what they do, and I said structure, I meant influence. Influence is how they shape the organization beyond position and structure. We know that position and function are weakening, that we are seeing them replaced by a more dynamic structure where people come and go, and where you work on an idea for a while and you move on to another one. How do we project and shape influence? And right now, the world has gone through a decade of realizing that influence is important, that not having processes that shape it and guide it is dangerous. Dangerous not only politically, but also in terms of your organization. It can turn your organization upside down. How do we put constraints on it to guide it? How do we make influences to use it well? Those are questions we don't completely understand. And what concepts are we starting to develop that go beyond that? The key thing we do know is that data is the point of innovation. That working with data is where we are seeing the most creative work, the most interesting work, and the most innovative work. That's not to say that old ideas of algorithm efficiency are not important. Yes, we still have people working on efficient algorithms, and we should, because there still remain questions to be answered. This doesn't dismiss architecture, because of course, we are constantly looking at architectures and new advances and how to restructure our computers to make them more efficient and more effective. But it does mean that the big field right now, and the one that's going to shape the next generation of leadership, is coming from something that's not viewed as traditionally part of computer science. Remember, we're looking at people, not things. Ideas, not necessarily hardware or situations. This is going to change our view of the world and change the view of ourselves. I argue it's going to be more global, more tightly connected. It's going to be more flexible in the sense that people will have a variety of jobs and roles that utilize their specializations, that specializations will shift, and that in particular, we will view ourselves not so much as a collection of fixed knowledge, but of fixed skills. How we deal with problems, how we gain new knowledge, and how we advance that knowledge to those around us. So this gets me back, since we're getting close to the end of the talk, what's the nature of computer science? And those three questions I posited at the start. What's the nature of the field? Who is a leader? And what's the intellectual foundation? The nature of the field, I think, is unchanged. And I think it's important that this talk push you in that direction. Herb Simon, a computer scientist from the early 60s, famously described it as the science of the artificial, the science of what can be mechanized. And if you have never read his little book, The Science of the Artificial, it's available freely on the internet. You can download it. It's a fascinating read, and I still think is largely relevant today. Because in designing mechanical systems, and computers are ultimately machines, he shows where the interesting points of design decision are and the kind of questions that need to be asked. And in particular, the relationship between the goal of the system and the underlying algorithms that make it work. That part of the field has been true since the 1940s and remains true today. It's expressed in new ways, but it is still part of the field. What's a leader? That has shifted over the years. And again, I want to emphasize that a leader, as I see it, is not one who necessarily controls money, although controlling money is part of it, is not necessarily in charge of organizations, because even though that is often part of it, it's someone who shapes the questions for research, the questions for products, the questions for applications, the questions for organizations. Back in the 40s, mathematics made you a leader. In the 50s and through 1968, I would say, electrical engineering made you a leader. The Computer Society was formed by the IEEE because they were recognizing that there was a new body of knowledge involving software that they needed to capture. And so we moved into that body of knowledge. There was efficiency in algorithms and software. We're moving into data. And the key thing to note is that we have always borrowed skills. We have always borrowed knowledge. And computer science has hardly ever touched anything without taking things from it. Our ideas on graphics have come from photography, from television, from films and movies. Our ideas about data have come from statistics and from a variety of other fields. We are now borrowing those data skills and expanding them. And it's that mastery that's part of computer science. So, what is that intellectual foundation? We borrow. We are an avaricious field, that we borrow things from every field we touch. In the first generation of leaders, we tend to reward generalists. We tend to reward people who are not necessarily highly specific, highly focused on one set of skills, but people who understand the broad framework and understand where a new set of skills fit into it. And as you're looking for leaders and as you're looking to become a leader, that's the balance that you're going to have to come up with. You're going to have to come up with a set of skills that's useful for immediate problems. And you're also going to have to look at how those skills fit into the entire field. So this is my talk. And I've been just so grateful to be here and so grateful I could be part of your first international conference. This is such an honor. But I really wanted to do this, as I've done for all my work as a leader in the Computer Society, to spur you to become leaders, because that's what you need to be, and that's what the world needs of you. We need you to say, this is what we see about our field. This is what we see about our applications. This is what we see about the needs of the world. And we are here to help get that done. Thank you very much.
Thank you, sir. It's very interesting and very fruitful. A lot of thoughts and questions and directions has been raised here. It's a very, very intense talk, by the way. It needs to be analyzed for a very long time.
And I will send you the slides so you can spend as much time as you want.
Yeah, thank you very much. But may I just point a very short point of view for the last two generations, the leadership of the third generation and fourth generation. You mentioned Steve Jobs and Mark Zuckerberg and so on. I think the leading edge came from empowering people. I think Steve Jobs and Bill Gates empowered average human being, average men and women to compute. And fourth generation, they enabled the world to provide and produce content. So I think the next thing, it will not be related to technology or mathematics or engineering or something, but what is the world needing to be empowered for? I think this would be a very interesting point and a major thing for defining the next 20 years leaders. If it's going to be 20 years, I think we will have two generations by then.
We may have to.
Yeah.
Yes, I think you are seeing it clearly and are clearly demonstrating that you're a leader right now.
Yeah. Thank you, sir.
There's certainly a part of social economics that is part of it. There's certainly part of sociology that's part of it. Certainly part of business and management that's part of it. I think you are seeing things clearly, and I look forward to your leadership role.
Thank you.
Yes, when we see you up there with Steve Jobs and with Mark Zuckerberg.
Yeah, thank you very much. Thank you. Yeah, if we have maybe more 2 or 3 minutes for questions, comments, Professor Khalid and
yes,
the colleagues, yes, please.
Yeah.
Okay.
Dr. Dia, if you want.
Thank you, Dr. David, for your interesting speech, and hope to visit us next year at our second conference in Egypt physically.
I will look forward to it.
Yes. If there are only one question from the attendees, say, Professor David, Can you discuss with us after gathering all data type and process it in a way it instruct us to live our lives? What would be the next stage? What might be the future shape or structure of data?
That's a good question. And this is where I can give you a broad outline, but details I don't know, and it's going to be for you to find. One of the lessons of the last 15 years has been where we have found data and how surprising it is what we can get useful data from, and things that we can make decisions and things that we can shape not only business, but government decisions and policy decisions and family decisions. I think part of it is going to be just, discovering in very, very simple things, activities and data that we didn't realize were important. The fact that tracing someone's path through their home or through their office and where they walk and where they move and what times of day they do it seems like nothing. It seems like nothing that's useful. But by capturing that and by aggregating it and by looking at it, we may discover new efficiencies, new ways of looking at things, new ways of handling it. Pictures, we've been doing things with, trying to find facial identification and trying to identify who's there. But being able to take pictures and capture motion, capture where people are going, capture time of day, capture other things that are there, may start revealing data that we hadn't, revealing ideas that we hadn't seen. I mean, in particular, facial recognition works on an interesting sort of plane. It works, in convolution of data. And we've started to crack that and understand that in certain graphical forms, but what other forms does that lead us to? And that's where I look to you, and that's where I get patient and say, show me where we are going, and I will be interested to find out.
Thank you, Professor David, for your answers. Prof. Khalid.
I think we have no questions, Professor David. So we extend really our thanks for you, for your favor and what you really presented to us through this meeting, and enjoyable meeting, really. So thanks again.
Well, thank you. And thank you so much. Have a wonderful conference. These things are so important for the field. Yes.
Thank you, sir. Let me again extend the honor and pleasure of Misr International University and the Computing Society in Egypt for having you, sir, such an honorable figure, and we are very honored, very happy to have you. Next time we will be face-to-face in Cairo after this pandemic, inshallah. So so we hope next year we can have you physically here in Cairo, Egypt.
And I would very much enjoy arriving in Cairo and meeting you all face to face. This has been my honor.
Thank you. It has been an honor and pleasure, personally for myself, for all my colleagues and university. Thank you, sir, for your kind support. Hope to see you soon. And thank you for all the attendees and panelists for the discussion and listening to such a big figure like you, sir. Thank you very much. Thank you.
Thank you.
Thank you. Thank you. Bye.
Thank you.
Bye.
تحياتنا للجميع، متشكرين يا فندم.
شكرا دكتور خالد.
شكرا يا دكتور ضياء.
شكرا.
شكرا دكتور أيمن.
شكرا يا فندم. I think we have maybe about maybe some 6 minutes or so to start the next speech. I think we already have Professor Elvira with us. Thank you for joining, and Professor Abdel Nasser will be chairing the next keynote speech. So we will start in 5 minutes from now. Thank you very much.
Thank you, sir.
الفيرا لو خرجت مش هترجع.
Can we start?
Yes, I think, Dr. Abdul Nasser, you have an echo on your microphone. So
Not my microphone.
okay, okay.
Yeah, exactly. Okay.
So we are going to start our next and final keynote speech delivered by Professor Elvira Popescu. Thank you, ma'am, for joining us today in our first international conference on mobile, intelligent, and ubiquitous computing. I'm extending the greetings and honors of the university for having you today with us in our conference. Professor Abdel Nasser Zaid will be chairing this session. And we have a lot of attendees right now, so I think it's going to be a very important and interesting talk. Thank you, ma'am. Professor Abdel Nasser, you may start. Thank you.
Thank you, Dr. Ayman. I am Professor Abdel Nasser Zaid. I would like to thank my colleague, Dr. Ashraf, our unknown soldier, Minnatallah, for her assistant. We have a very famous keynote speaker, Professor Elvira Popescu. I think I read the name correctly. If we introduce Professor Popescu, I think we need many hours, but I will try to summarize as much as I can. Professor Popescu is a full professor of the Computers and Information Technology Department, University of Craiova in Romania. Professor Popescu received her PhD from Romania and France. Also, she serves as a vice chair of IEEE Women in Engineering Romania section, affinity group, and is an executive board member of IEEE Technical Committee on Learning Technology and the International Association of Smart Learning Environments. Professor Popescu has many publications. It's about 10 publications, including books, journals, conference papers. Her research interest, technology enhanced learning, adaptation and personalization web-based system, learner modeling, computer support, collaborative learning, learning analytics, and intelligent and distributed computing. Our topic is learning analytics, a multiple perspective analysis of student data. I have the honor to introduce and give the chance to Professor Popescu to give her our talk to us. Please, Professor Popescu, start your presentation within about 40 minutes and leave about 10 minutes for discussion. I think all of us are interesting to hear from you, Professor. Okay, go ahead. Okay.
Good afternoon. I hope you can hear me.
Okay.
Thank you very much for inviting me. It is an honor to give this keynote talk. I'm going to share my presentation. And I hope that you can see it.
Yes, okay.
Okay. So one more time, thank you. It is my great pleasure to talk about learning analytics and try to provide multiple perspectives analysis of student data. Just to give you an idea of where I come from, Craiova is a Romanian city about 200 kilometers west from the capital, from Bucharest. Here you can see the main building of our university, which is quite large. It has more than 20,000 students and is one of the top 5 composite universities in Romania. So what I'm going to talk to you today, I'm going to start with an overview of learning analytics. Then I will share our experience in the context of a social learning environment, which is based on multiple perspectives. And I will try to briefly describe a few of them starting with a solution proposed for student performance prediction, followed by the application of social network analysis for exploring students' collaboration patterns, and then by a content analysis approach based on community of inquiry model. And finally, I will end with some challenges and trends in the area of learning analytics. So starting with a brief overview of learning analytics. The area is very timely and growing, and it aims at selecting, analyzing, and reporting student data in their interaction with the online learning environment, finding patterns in student behavior, displaying relevant information in suggestive formats, all with the goal to predict the student performance and to try to optimize the educational platform and to implement personalized interventions. And you can also see here a formal definition provided by the Society of Learning Analytics Research, according to which learning analytics represents the measurement, collection, analysis, and reporting of data about learners and their contexts for purposes of understanding and optimizing learning and the environment in which it occurs. And the topic is very or highly interdisciplinary. It includes machine learning techniques, educational data mining, statistical analysis, social network analysis, natural language processing, but also knowledge from learning sciences, pedagogy, and sociology. And learning analytics can be defined at several levels. We can have micro-level analytics, which refers to the tracking and interpretation of data for individual learners or groups, with the goal of identifying and helping students at risk and trying to provide personalized recommendations and raising students' awareness. Then we have meso-level analytics, which operate at institutional level, aiming to better understand the challenges and successes of the institution and trying to improve administrative decisions and resource allocation. And then we have the macro level analytics, which is cross-institutional at national or international level, having the potential to have an impact on the academic models and pedagogical approaches. And in this talk, I will focus mostly on the micro-level analytics. But of course, when aggregating all kinds of individual learner traces, this has the potential to enrich also or to inform also the meso and macro analytics. There are also various tasks that can be supported by learning analytics and several objectives that it aims to fulfill, such as monitoring and analysis, prediction and intervention, tutoring and mentoring, assessment and feedback, adaptation, personalization and recommendation, as well as the students' reflection and self-awareness. And one of the most popular goals of learning analytics is the prediction of student performance. So this means trying to estimate future learning outcomes and identify indicators for learning success. So basically the objective is to develop a model which can infer students' academic performance, so the so-called predicted variable, which is generally a grade or a score, from a combination of various indicators, which are the predictor variables. And the popularity of this student performance prediction comes from the value of the information that it offers. This kind of information can be used for advising the instructor about students at risk who need more assistance. Also, it can offer the instructors the ability to monitor the learning progress and to provide personalized feedback and interventions to students in any performance state. Also, individualized strategies for improving participation may be suggested. We can also envision a formative assessment tool based on the automatic prediction mechanism. And finally, as I was also mentioning before, students' awareness can be increased by providing them with the prediction results and personalized feedback. So far, performance prediction has been studied extensively in web-based educational systems, and in particular in learning management systems, due to the availability of the large amounts of data which are logged by these systems. Also, performance prediction has been applied in intelligent tutoring systems and more recently in massive open online courses in MOOCs, but less in the area of social learning environments. This was less investigated as a potential performance predictor, and this is what I'm going to address in this talk. So now a few ideas about our research experience in this area. So our goal was to investigate this less explored context of social learning environments, and we focused specifically on a platform that we developed in-house, which is called eMuse, Empowering Mashups for Socially Learning. The platform provides integrated access to various social media tools selected by the instructor, such as blog, wiki, Twitter, media sharing tools, social bookmarking tools. And it provides a common access point, detailed usage instructions, summary of the latest activity, various basic administrative services, also evaluation and the grading functionalities. So how the platform works, it retrieves students' actions with each tool and stores them in a local database. And then it provides a summary of each student's activity, including various graphical visualizations, evolution over time, comparison with peers, and aggregated data. And we used the platform for 7 years. So this means with 7 student cohorts, with a total of 375 students from the University of Craiova. The study took place in the context of an undergraduate course on web applications design. And the instructional approach was project-based learning, in which students worked collaboratively on various complex tasks over a whole semester. So the learning was organized around projects, and the teacher played more a role of a facilitator. So basically, students collaborated in teams of around 4 peers in order to build a complex application of their choice, such as, for example, a virtual bookstore, or some of them chose to implement an online auction website or an online travel agency, or things like that. And we had a blended learning approach consisting of weekly face-to-face meetings between the members of the team and the instructor. And for the rest of the time, students had to rely on the social media tools as a support for their communication and collaboration activities. So more specifically, they used MediaWiki for collaborative tasks, for gathering and organizing the team resources, and for documenting the project. They also used Blogger for reporting the progress of each project. It was used as a kind of a learning diary for publishing ideas and resources, and for providing feedback and solutions to students' problems. And Twitter was used for fostering some additional connections between peers, and for encouraging the posting of short news, announcements, questions, status updates regarding the project. And as I mentioned before, all the student data, so all students' contributions on the social media tools were collected by eMuse platform. And our objective was to analyze this data from multiple perspectives in order to get a more comprehensive understanding. So we explored academic performance predictors, the relationship between students' learning styles and their social media use. We also investigated students' collaboration patterns and the community of inquiry supported by social media tools. And more specifically, we tackled 4 main research directions in learning analytics, referring to analytics dashboards, predictive analytics, social network analytics, and discourse analytics. As far as the analysis techniques are concerned, we applied various approaches such as classification, regression, clustering, and PCA algorithms. Also textual complexity analysis, social network analysis techniques, and content analysis based on the community of inquiry. So overall, we try to address the so-called trinity of methodological approaches: network analysis, which refers to actor-actor or social interactions, relations; process-oriented analysis based on action logs and pattern detections; and content-oriented analysis based on learner-created artifacts. And in what follows, I will present a few of these approaches briefly, of course. And I will start with student performance prediction. So for this particular analysis, we took into account 6 student cohorts with a total of 343 students, with almost 19,000 social media contributions, so over 2,600 blog posts and comments, over 5,400 tweets, over 10,800 wiki page revisions and file uploads. And based on these actions, we computed a set of 14 numeric features or indicators for each student, as you can see here, and they refer, as you can see, to various relevant quantitative characteristics, which can be computed based on the recorded student actions, so number of posts and edits, the length of the content, the time distribution. And as you can see, these actions refer to various types of learning activities. So creating and organizing content, social interactions, communication, and feedback. So the idea is that they mainly represent tacit student actions, which are not generally assessed as a part of the learner's educational progress. So they are not those classical explicit student actions, such as completing an assignment or taking an exam. Of course, they are still only quantitative indicators, so they don't take into account the quality of the learner actions. But still, we consider that they are a good measure of the level of involvement of the student, especially if we take also into account the number of or the level of involvement of the students throughout the semester. And finally, the students' performance at the end of the semester was assessed on a 1 to 10 scale. 5 was the minimum passing mark, and our aim was to predict this final grade based on the set of features. And for that, we proposed a novel algorithm called large margin nearest neighbor regression. I will not get into the details of the algorithm here. You can find them in the open access paper here. So just a brief general description of the algorithm. Generally, in a classification context, support vector machines rely on the idea of finding a large margin between classes by solving an optimization problem. And the idea was used in conjunction with k-nearest neighbor methods to change the distance metric of the KNN space. And this method was further developed for regression purposes, which resulted in an original algorithm, the large margin nearest neighbor regression. The optimization problem takes into account two criteria. The nearest neighbors of I should have similar values to the one of I, and more distant ones should have different values. And the distance to the neighbors with close values is minimized, while also trying to maximize the distance to the neighbors with distant values. And in order to assess the performance of this algorithm, we conducted a comparison with the algorithms implemented in WECA. We tried various algorithms belonging to different classification and regression paradigms, K nearest neighbors, neural networks, decision trees, support vector machines. But the best results were obtained with these two algorithms, with random forest with 100 trees and K nearest neighbors with K obtained by cross-validation and inverse distance weighting of the neighbors. So in the table, you can see the correlation coefficients obtained by the three algorithms for each data set. So for each of the 6 years, plus all the years combined, plus all the data normalized by year and then combined. And as you can see, our algorithm clearly outperformed the other algorithms on all the 8 data sets. And here you can see a comparison between the predictions of the model and the expected data for all the years combined. So in the left-hand chart, you can see that the scale is the interval 0, 1. This is because all the data was normalized attribute-wise before applying the algorithm. And you can also see on the right-hand chart the normalized results converted back to their initial domain, so to integer grades from 3 to 10, where once again 10 was the best grade. And the correlation coefficients in the two situations are very close. But of course, by rounding, as you can see on the right, some information is lost and R is slightly lower. And here you can see the errors of the models as actual differences between the predicted and the desired values. And we could notice that on average, 85% of the predictions were within 1 point of the actual grade, which means that the algorithm was capable of a good approximation for our problem. And in case of the combined years, so on the right-hand side figure, you can see that the errors are slightly higher. So here, 79% of predictions are within 1 point of the actual grade, and 96% were within 2 points of the actual grade. But in any case, as you can see, the number of errors for the difference for -4 and for 0 was 0, and for -3 and 4, it is only 1. So again, pretty good results. And of course, one of the main motivations for analyzing learning data is the ability to predict student behavior as early as possible in the course. So we tried to assess how useful the trained models are for predicting the student behavior in future years. So basically, we trained the algorithm on data from earlier years and tested its prediction performance on data from later years. And as you can see here, the obtained correlations are comparable to those found for all years combined. But there is a difference, a small difference. In the previous case, we used cross-validation for the same data set. And in one fold, 90% of the data was used for training and 10% for testing. While here, the whole data set of a year is used for training, and the whole data set of another year is used for testing. So the problem is thus more difficult. And you can see here in the table that even if different years have different characteristics, there is also a large degree of consistency. So an existing model can be used to anticipate and to correct or to enhance some student trends once they are identified. So the study basically shown that students' actions on social media tools are good predictors of academic performance. And the innovative algorithm proved very suitable for our prediction problem, outperforming classic regression algorithms. And again, we obtained very good correlation coefficients. As I was mentioning, 85% of the predictions were within only 1 point of the actual grade. And from a pedagogical perspective, the results show that, as a general rule, a higher engagement with social media tools correlate with a higher final grade. And this is in line with several other studies which show that online participation is a good or a strong indicator of student performance, and it can improve learning effectiveness. It is also worth mentioning that the performance of the generalized predictive model, so from all 6 years combined, is slightly lower than the performance of each individual year model. So this is because each year has some specific characteristics which are caused by the particular dynamics of the students. And also there were some small refinements and improvements from one year to the other based on the feedback that we received from the students and from the instructor. But still, we can see that there are clear common characteristics of the 6 years. Otherwise, of course, the correlation coefficient would be much lower. And so this is basically an interesting result, which shows that the behavior of students that belong to different years of study present a combination of stable and variable elements. And this is, of course, a current challenge, an open challenge in learning analytics, the issue of aggregating trace data from different courses for creating one generalized model for academic success prediction. So there are various differences in instructional conditions or in technology use, even when we are talking about the same discipline or the same course, which can influence the prediction of academic success. And also other characteristics, such as, for example, some individual differences between the students involved in the studies. These may also have an impact on the learning analytics results. Okay, and now I will move on a bit more quickly to the next learning analytics approach, using social network analysis to explore students' collaboration patterns. So as you probably know, social network analysis is a cross-disciplinary research field which explores social environments that can be modeled as graphs. The aim is to offer an insight into the structure of online learning communities, various communication aspects, and patterns of academic collaboration. So what we did was to build a directed graph starting from students' interactions on blog and Twitter. And we studied the differences in collaboration patterns supported by the blog versus Twitter, intra-team versus inter-team collaboration. And also we tried to offer various other in-depth student and team analysis. So this is a graph which depicts all social media interactions among students. So the vertices represent the students, the links represent collaborations among them. So the messages which were exchanged through the two social media tools. The size of each node is proportional to its eigenvector centrality value. And the color of the nodes depicts students clustering as determined by the modularity algorithm. And finally, the links are colored according to their source node. And here you can see a comparison between the two graphs, the blog graph and versus Twitter graph. Of course, we also performed some more analysis with various social network analysis metrics, such as number of links, average degree, diameter, density, modularity, and so on. But I will not get into the details here. You can see them in the journal paper as that I was mentioning before. So now I will just mention the main results. So what we found out is that both social media tools provide an adequate support for collaboration, and Twitter supports both inter-team and intra-team interactions, while Blogger supports mainly intra-team collaboration. For all these analyses, we used Jeffy network analysis tool, which was very adequate for our research needs, but it was perceived as too complex for the instructors, who of course are not specialists in social network analysis or visualization. So that is why we decided to build a simple network visualization tool, which is easy to use by the teachers and was specifically designed to work in conjunction with our MIUCC social learning environment. And this is how a StudentVis tool was born. So basically the tool tries to provide intuitive visualizations from the instructor's point of view, such as the general status of the collaboration, also the collaboration of for each community and for each learner. And here you can see on the left-hand side figure, the visualization with students with nodes diameters proportional to the PageRank metric and the colors depicting the affiliation to a team. And this figure aims to provide the instructor with a general overview of students' collaboration and their relative collaboration status. And the nodes which have a central position and larger diameters depict learners which have a higher collaboration status. And on the right-hand side figure, the lower figure, you can see the inter-team collaboration status. So we have nodes which represent teams this time, and their diameters are proportional to a PageRank metric. Okay, so so far we considered only student posts and student interactions from a quantitative point of view. So no consideration for the actual content of the student contributions. So what I will present now is an analysis of the content according to the community of inquiry model. This model, for those of you who are not familiar with it, was proposed by Garrison, Anderson, and Archer in the year 2000, and has been used extensively over the past 2 decades for exploring the development of online learning communities, and more recently also for the communities supported by social media tools, as is our case here. And these communities can be characterized in terms of 3 interdependent components. So we have, on one hand, the cognitive presence which represents the extent to which learners can construct meaning through reflection and discourse. Social presence, reflecting the ability of learners to identify with the community and develop interpersonal relationships by projecting their personal characteristics into the community. And finally, the teaching presence, which refers to the design, facilitation, and direction of cognitive and social processes to support learning. And later on, in 2010, Shea and Bejarano suggested the extension of the community of inquiry model with an additional construct, which they labeled learning presence, which refers to learner self-efficacy and also self-regulation and co-regulation. So basically, the active role of the students in terms of metacognitive, motivational, and behavioral traits. So our aim, as I was saying, was to explore how the social media tools, and in particular blog and Twitter, can support a community of inquiry between students in a university or in a higher education context. And in order to support the content analysis procedure, we designed a dedicated tool for content annotation based on the community of inquiry, which we call the Call Annotator. The tool retrieves students' content, so the blog posts and tweets from the EMU's database, and then generates various reports and statistics which are specific for our instructional scenario. And you can find more details about the tool and also about the research questions and results in this open access paper. And now just a brief overview of the findings. So in the first figure, you can see the number of blog posts pertaining to each presence. So this is a graphical representation which was generated by the Call Annotator tool. On the left, it is taken into account only the primary category associated to a post, and on the right, both the primary and the secondary category, if they are available, of course. And on the bottom figure, the same thing, but for Twitter. So as you can see, the overall distribution of presences is quite different between the two social media tools. So when we take into account only the primary category, we see that cognitive presence is dominant on the blog, but less apparent on Twitter. Also, the learning presence is dominant on Twitter and less represented on the blog. And if we consider also the secondary category, we find out that social presence becomes dominant on Twitter, but less apparent on the blog. And finally, as you can see, the teaching presence is scarcely exhibited by the students on either of the two social media tools. And Call Annotator also provides us with the temporal evolution of students' contributions on blog and Twitter, as you can see in these figures. So first of all, you can notice that the weekly amount of posts follows a somewhat similar pattern between or both on blog and on Twitter. And for within each tool, the weekly patterns of each presence are relatively similar, showing a balanced distribution throughout the semester. So overall, we can see that the students used the social media tools throughout the semester, and they thus tried to contribute continuously to the formation and growth of the community of inquiry. So according to this content analysis, we found out that the blog plays the primary role of a content space, as the cognitive components clearly outweigh the social and learning components. On the other hand, Twitter is mostly a discussion space, supporting especially the learning presence and the social presence, while the cognitive presence is less strong. So we can conclude that each tool fulfills its own distinct role in the learning space, providing a complementary support to the community of inquiry. And a special mention should be made regarding the teaching presence, which was very weak in our study. It was left as the preserve of the instructor, of the teacher. Conversely, the learning presence was apparent in numerous blog posts and tweets. So this was just an overview of some of the research directions that our group performed in the area of learning analytics. And now I would like to conclude with some general challenges and trends in the field. So one challenge refers to transferability. So students are currently using various systems for learning in different years of study, sometimes even for different courses in the same year of study. And it should be possible to transfer the student model from one system to the other and be able to use that information in order to improve the current student model. Another challenge refers to effectiveness. So currently, platforms are able to infer which students are at risk, for example, based on the learning analytics from learning management systems data. And these can and are used to support the students, for example, by offering them targeted interventions. But the problem is that this is generally just a short-term solution, so for the duration of one course. And it would be needed to have more durable changes and interventions to produce long-term successful outcomes. Another challenge refers to interpretability. So predictions should be intuitive for the user, be it the teacher or a student, and the models that they are based on should be interpretable, should be scrutable, so that users can understand and trust these models. The applicability of the models is also a very important issue because models should be able to work in real-world complex contexts. So not just when we are talking about one student which sits at one computer and which provides simple textual input. We can have, and we normally have in our learning process, several students learning together in the same physical space, interacting with various tools, and also interacting directly with one another. So not only interaction mediated by computers. Another challenge refers to generalizability. So models should be able to work across courses and across systems. So ideally without having to refine or to tweak, to make modifications to the initial models. And also, this is something that I have presented also in this talk. And also, models should work on different types of populations. So generally we use a convenient sample. We just use for evaluation the students at our own university. But the models should be able to function well also for completely different samples. So from various students with variations in terms of race, ethnicity, native language, citizenship, economical status, and so on. Another important issue refers to ethical and ethics and privacy. Ideally, we should find a suitable way to meet high ethical standards and to ensure a beneficial outcome for all the stakeholders. Because what happens now is that a lot of the literature, a lot of the papers have a teacher-centric or an institutional-centric view. So instead, it would be ideal to focus on the students as primary stakeholders, and they should be consulted in the development and the application of learning analytics. So instead of just assuming that we know what students want or how the data, how they would like the data to be presented, it is better to directly ask them. And now the final three refer to mostly future endeavors in the area. One relates to lifelong data integration. So currently, learning analytics is mainly based on the interaction of students with only one educational environment. And instead, data could be gathered from multiple available sources, not just from previous educational environments, from previous institutions, but also from the personal status of each student from different points of view, familiar, economical, emotional, psychological, and so on. Then we should also take into account the emerging educational environments, because due to the advances and the innovative technologies which were developed lately, we also have a new generation of educational systems, mobile and ubiquitous, based on virtual reality, based on augmented reality, and so on. And of course, learning analytics needs to be applied also in these cutting-edge environments. And finally, it would be interesting to analyze and mine also brain data, so data gathered directly from students' brains based on the brain-computer interfaces. So this way we have great opportunities for collecting, sharing, and manipulating all this kind of information gathered from the human brain. So as you can see, the field of learning analytics is very dynamic, very complex, continuously evolving. So I hope I was able to provide some small insight into the area in this presentation. And I will end here. And of course, I would be happy to discuss if you have any questions or comments. And for more information, this is a list of references. You can find all the papers on my website. And of course, yes, last but not least, I would like to acknowledge all my collaborators, both students and colleagues who contributed to this research. Thank you.
Thank you, Professor Elvira, for this interesting and excellent presentation. Especially, it covers a hot topic now during the COVID-19 pandemic and the needs to study or focusing on the emerging technological emerging technology and educational field and how to use it. But let me ask you one question about your model. You talk about you study the performance of about more than 300 students. What about the level of these students? I mean, your model can be used for higher education students and lower, I mean, in secondary school level. Again, it is maybe possible to use your model with students study science and technology or study humanities. Which one maybe is the best? And I will give the floor for the other colleagues to ask you, but can you answer, please?
Okay. Thank you for the question. So we applied our model for higher education students, third year computer science students from the University of Craiova. So we were not able to test it on other student populations. As I was mentioning, this kind of generalizability issue is very important in learning analytics. So what we found out was that models could be used from one year to the other successfully, but only within the context of the same course. So unfortunately, I cannot give you right now an idea of how the model would fit for different courses or for different levels of the students. So this is indeed an important issue, trying to transfer the models from one context to the other, from one type of student population to the other. This is still an open challenge.
Okay, thank you. At least we have a channel to make researches with together about this your model and how to use it in different levels, different study subjects. Again, about our participants and colleagues, anyone have questions?
Yeah, actually, I have a question.
Yes.
Professor Elvira, thank you so much for your interesting presentation. Actually, I'd like to ask a question regarding the contextual analysis for you students' posts on social networks. Have you applied any contextual analysis for such questions or such posts to see if there is a relation or direct or indirect relation of the emotional analysis of these texts or contexts and their performance?
Okay, Professor.
Sorry, I think I have not heard the last part of the question very well.
Well, I will ask again my question. Regarding the student assessment, have you applied any contextual analysis for students' posts which may reflect the emotional status of the students, which may affect directly or indirectly their behavioral?
Mm-hmm. So yeah, this would be a very interesting area, trying to apply effective computing techniques. We did not use this kind of analysis so far. What we did instead was ask students to fill in various questionnaires at the end of the semester. I did not present this analysis here. I just focus on three of the analyses that we have performed. And in those questionnaires, we also asked them about their level of motivation. And we did some correlation analysis between the level of motivation of the students and their performance in the courses. And I can send you the paper which refers to this particular issue. But as far as emotions are concerned and effective computing, no, we did not perform this. And I think this would be a very interesting future direction to look to.
Well, thank you. Thank you so much.
Okay, Dr. Ammar, can you ask? Dr. Ammar.
Thank you, Dr. Abdel I would like to ask the same question, almost like the question of Dr. Islam. Thank you, Professor Popescu, for this wonderful talk. In particular, you showed us how to show the analytical the learning on different levels. But from psychological perspective, there is a lot of consideration that tells there is the emotional behavior is one of the strong predictor of a student. Is there any kind of work that involves not only the student metadata or the student data, but also to engage the emotional or the facial expression of a student, especially we are now in pandemic and all the students are living in isolation. If there is some sort of work that consider the emotional behavior as a strong predictor in engagement of student performance? Thank you.
Thank you. Thank you for this question. Indeed, this kind of multimodal analysis is very, very interesting trend nowadays. So aiming to capture data from various types of interaction modalities in a meaningful way, including emotional status of the students. As I was saying, we did not touch this issue, but we did take into account some other individual differences of the users to the learning style of the students. So maybe you are familiar with it. It is one of the most used models in engineering areas. And we did perform some correlations between the students' learning style and students' performance on one hand, and also students, we performed also textual complexity analysis on the students' contributions and analyze the correlation with the students' learning style.
Okay, thank you, Professor Elvira, and thank you for.
I managed to answer your question. Thank you.
Okay, thank you, Professor Elvira, for your comments, for your presentation. And I think for further communication, the colleagues can use your email. And thank you for your participation. And now we should leave to allow for the next session. Thank you again and welcome. Bye-bye.
Thank you, sir. Thank you, Professor, for your.
Thank you one more time for having me here.
Yeah,
thank you, and have a successful conference.
Thank you. I'm extending again the honor and greetings from the university to you, Madam, for joining us today. Thank you very much. Thank you for all the attendees, and hope next time it will be physical in Cairo.
That would be great. Thank you one more time.
Thank you very much. Thank you. And yes, we are going to move to the technical sessions in 2 minutes. Thank you very much.
نعم أنا قفلته وبعدين فتحته.